Welcome to the third of our little momentum help videos. And what we're looking at here is another situation where we can apply conservation of mass. And this situation, though, is separately known as an explosion. And just as in the last video, we are still working on the basic idea that since the total mass of a system times the velocity of the center of mass will not change, because if I have two objects before, I'd have mass of object 1 plus times velocity of object 1 and mass of object 2 and velocity of object 2. This setup can't change. So if I look at it later, some v final 1 for that first object and v final 2 for the second object, since the velocity of the center of mass and the total mass, if these haven't changed because we've had no outside forces, then the momentum before will equal the momentum after. And the total momentum must stay the same. Well, what that looks like here then is if this clown is initially motionless, the clown and the object together start out as basically one. They are stuck together. Mass 1 plus mass 2 times v original. So we can group them and say, hey, the velocity of the center of mass of this system, of the clown and the barbell, well, they start out motionless. So this total momentum would have to start out being 0. Now, after they separate, the clown gets pushed in one direction and the barbell's going in the other, but we can say, since we are unable to create momentum from nothing, for every bit of momentum that the clown gets in one direction, the barbell will get in another. Now, if this is going to be 0 over here, one of these will have to be negative. Now, I'm skipping to the equation here because I want to emphasize this concept. Let's see what this looks like in the problem-solving context then. If we start out, we say, all right, I want to know the mass of the barbell, mass 2. I know the mass of the clown is 80 kilograms. I know the velocity original of both the clown and the barbell. We could say v original 1, v original 2, or whatever, or just total v original, is 0, which also happens to be the velocity of the center of mass. So this whole side of the equation will end up being 0. We know that v final 1 for the clown has to be 0.5 meters per second. And let's say that this is to the left. The barbell is thrown forward with 10 meters per second. Let's say that's to the right. Now, it doesn't matter which is left or right, but it's important that one of those is opposite. And since we have opposites here, one of these needs to be a negative. So let's make sure that we include that. Will you always have a negative in problems? No, it's not guaranteed, but anytime we have opposite directions, then you should be looking to include that negative. Now, with this in mind, we have everything that we need to solve this equation over here, especially since we get this big 0, and now all I need to do is solve to get our mass 2 alone. If I do that, mass 2 ends up being mass 1, v final 1 for the clown, divided by, with a negative, we had to subtract to get it over there, divided by v final 2. It should make sense, I hope, that what we're doing here is basically taking the backwards momentum of the clown, mass times that backwards velocity, and we're just dividing out the velocity of that barbell, knowing that we have the momentum on top, divide out the velocity, and we should get mass. So 80 times our 0.5, the negatives cancel out, multiply out, and 80 times 0.5 divided by 10 should get me 4 kilograms. Now let's do a quick check to just make sure that this answer makes sense given the rest of what we have. The, if we have these two momenta and we know that they should be equal and opposite, and the clown has 80 kilograms, quite a bit of mass, and a low velocity. We have a large velocity for our barbell. Should our mass for the barbell be greater than or less than the clown? Well, we have large mass times small velocity, and large velocity times small mass. Those could work out. We should have a mass less than 10 kilograms. We do get that, and we do see proportionality there. All right, so this is, if you look around you, you'll see plenty of examples of this explosion principle, that we can have two things that can start out with zero momentum or just some set momentum, and both objects can experience large changes in momentum even as the system as a whole stays the same. Thanks for watching. Good luck. We'll see you next time.